Hour and a half this morning, and I promise I'll try to make it as exciting as possible, is what batteries actually are. So I work for North Star now. I've been in batteries for about 10 years. As Dan said, my background's in chemical engineering and mathematics. So, and I spent my first few years working with Mintronics, dealing with all the battery manufacturers. So what we're going to talk about this morning isn't about North Star. It's not about anything specific to North Star, but it's about all batteries in general. So we want to cover, first of all, what batteries are, how they're made, how they're constructed, and then we'll talk a little bit about the selection process of why certain batteries fit in certain applications better, and we'll talk a little bit more about testing as well. Okay? Any other topics anybody wants to cover on batteries? No? If you come up with anything, please raise your hand. Do this. I get a little passionate about chemistry, as you'll find out. In fact, most of the guys don't like me to tell them the jokes that I think are funny because they're chemistry jokes. But that type of stuff to me is very exciting. So if I seem a little bit too passionate, feel free to tell me to calm down. But if you want any more information, please do not hesitate to ask.
You talked about battery recovery rates and the difference between the different types of batteries and the rates that they recover at.
Absolutely. And that's the cool part of batteries is in 1859, the lead acid battery was actually created, the very first one. So it's been around a long time. The ones we build today are not drastically different than the one built in 1859. The core chemistry of it is the same. So the cool thing about batteries, and I always start out with this slide whenever I'm talking about lead acid batteries, because the one question everybody asks me is, well, what's the next thing? What about lithium ion? What about lithium phosphate? What about sodium batteries? What about all these other battery technologies that are out there? What about them? They're good. I bet you, does anybody know when lithium batteries actually first started? When they hit the marketplace in production? Does anybody? Chet? Do you know?
No.
Dan, do you know?
No.
70s?
1992.
Oh.
It's been around for 25 years. They're not new. Now, there's a reason why they're not predominant, and they're not in every fire truck, and they're not in every car, and that's just because it's not the right fit for everything. Lead acid batteries have been the one technology that have done a couple of things for us. Number one, everything's readily available. But more than that, 99% of all lead acid batteries are recycled. 99%. And that's all the components of it, 99% of them. Now compare that to only 26% of tires are recycled. 26% of glass bottles are recycled. Everybody thinks glass bottles are all recycled, only 26% of them. 45% of newspapers are recycled. I don't know which one's correct, 45 or 55. 55 is something else, I can't remember what it is. But when you look at those common things that are often recycled, batteries are recycled even more. And we're talking about lead acid batteries specifically. Lithium ion batteries cannot be recycled. Or at least it's too expensive to recycle. So they're not recycled. Lead acid batteries are here. We've been making them for a long time. They're going to stay around for a long time in the future. The new technologies and batteries that are coming out, there might be some new stuff that comes out. Capacitors, which aren't actually a battery, but ultra capacitors are out and have been for a number of years. Lithium ion cells, lower voltage ones, higher voltage ones. They're not going away, but there's going to be a lot more development on that side before they even come close to taking over lead acid batteries. Does anybody have any questions on where lead acid batteries are and why lithium's not taking over and all these other battery technologies?
So where do they put the lithium? Is it just in the landfills, or I mean, how do they get rid of the batteries?
A lot of them are buried, unfortunately. Yeah. Well, lithium, you'll never hear lithium talk about how they're recycled and things like that because it's just too expensive to do it. And frankly, the lithium part of the battery is such a small amount. And right now there's an abundance of lithium being mined for what we need batteries for. The demand's not there. Now, there's a lot of studies out there that say by the 2020 and some years after that we'll be short on lithium. to drive up pricing. But all batteries are built the same way, okay? And we'll go through how a battery actually comes to be a lead acid battery. But every battery, doesn't matter if it's lithium or what it is, works off an electrochemical storage, okay? Electrochemical, all it is taking electrons. Anybody remember chemistry from high school? Drawing the atom, and you got the nucleus of the atom, and then you got the electrons that circle around it. The outside electrons for any atom of any element are called valence electrons. Those electrons can move from atom to atom. It's how we get molecules and things like that. And for instance, water, H2O. They're, the two hydrogen atoms and the one oxygen atom are actually sharing electrons. And that's what makes it a molecule. That same concept is used in every battery. You take two dissimilar metals or elements, atoms, and you force electrons into them to create a molecule. And it gets held in there. It doesn't want to be in there. The electron doesn't want to be there, but it gets held in there. It's like shoving it in and then not giving it a pathway out. As soon as you give it a pathway out of that molecule, guess what the electron does? Shoots out. That's what a battery is. It's just the storage of those electrons. Now, we make lead acid batteries work off of one chemical equation and store 2 electrons in its base form. A lithium reaction will actually store up to 10 electrons in its base form. So depending on the chemistry of the battery, that's how many electrons we're storing. And if you think about it, a lithium battery, they catch fire, right? You've read the news and things like that. It's because they're storing such a high amount of electrons and they're shooting out of the battery so fast. If they short out, if something happens to it, the amount of electrons or electricity coming out of it is coming a lot faster than a lead acid battery. That's also why a lithium battery takes a much smaller amount to create a high voltage. Because voltage is that pressure of the electrons trying to get out of the battery. Okay? I'm going all over the place, so I'll pull it back. On the lead acid battery side, we have developed a lot of new technologies that use the core chemical reaction. Okay? Flooded batteries are what we've all known for the longest time, right? And in the 70s, we came out with maintenance-free batteries. Batteries that you didn't have to add water to. The difference in those batteries, and we'll talk a little bit about it later, but there's an element called antimony that was added prior to maintenance-free batteries. That element in the chemical reaction consumed a lot of water. Therefore, your water level would lower. You'd add water back to it, and it'd have to be distilled water to bring your water level back up. Maintenance-free batteries no longer use antimony. They use calcium. That calcium doesn't consume as much water during the chemical reaction, and therefore you don't have to water it. Therefore, maintenance-free. We've had maintenance-free batteries for probably most of all of our lifetimes, right? Now, new technologies that have come out, enhanced flooded batteries. Anybody ever hear of enhanced flooded batteries? Probably not. This is big in Europe. This is the concept of taking a regular flooded battery and adding a whole lot more plates to it and squeezing them closer together and try and get more capacity out of the same technology. That's enhanced flooded. We also have AGM batteries. Okay? Those have become really predominant recently. Do you know when the first AGM battery came out? It was actually developed by Gates Rubber Corporation in the 70s. It's been around for a long time. But it's been developed and mass produced in the past 10 to 15 years. You've heard a whole lot more about it. Now the newest thing that has come out, and this is really getting a lot of play in marketing materials, and you'll hear me talk about, there's two sides, in my opinion, of the battery business. You have the technical side, and you have the marketing side. And typically there's a technical side that makes all the batteries work, and they design all the batteries, they do everything. And then you have the marketing side, which takes bits and pieces of what the technical guys say and put it in marketing form so it sounds great. One of those marketing words that has come out recently is carbon, and using carbon additives. And Dan and I have had this conversation multiple times. It's nothing new. So what the most expensive part of a battery, anybody know what it is? The plate, which is made of lead. Lead's expensive. It's actually up right now. It's well over $1 a pound right now. Is it coming down?
5 cents today, it's
5 cents today.
96 cents.
Us battery guys, we really watch lead because we make a lot of, in fact, in this battery that weighs 76 pounds, there's over 53 pounds of lead in it. So lead is the major component of the battery. But in any case, so anytime we try to figure out a better way of building the battery, we like to add things to it, to start taking out a little bit of lead, and we try a lot of different things. Carbon started being added a few years back as a negative plate expander, a way that we could put carbon in there. Carbon doesn't react with a lot of stuff, so it's not going to damage the chemical reaction of the battery, so they put it in there to try and save a little bit of lead. What we found was it's actually a great additive. It actually promotes longevity in the battery. So that's a new technology a lot of people are talking about in carbon. Almost everybody is utilizing some form of carbon in their plates. So as an expander. So it's just some guys are marketing it better than others. The marine marketplace is big on carbon. That's a big marketing term there. So let's go back a little bit and talk about the electrochemical basics that have to do with the battery. Okay? First of all, we talked about the electron. The next one that we'll talk about a lot is active material. Active material are the things inside a battery that actually make the battery work. So anything that is used in that chemical reaction every time the battery cycles is active material. Everything else is a non-active material. It's not really needed. It's there for some other reason other than energy storage. So we've got the electrons. We have the active material, which stores the electrons. And then we have the equation. In my opinion, this is the most important part. If you take nothing else away from today, understand the basic equation of every lead acid battery. Because if you understand that, everything else, when we talk about recharging, when we talk about all the testing, when we talk about everything else, it all ties back to here. Dan and I were down in Hawaii about, it was probably 2.5, 3 years ago. And we had a battery that was leaking acid out on the top. And we actually went back to the chemical reaction, drove it back from there to figure out what the problem was with the battery. Everything goes back to this chemical reaction. That's why a chemical engineer is in batteries and loves batteries. Loves batteries, probably shared a little too much. Now you think I'm kind of weird, but that's okay. So, this is a fully discharged battery. When a battery is completely empty, no storage of electrons whatsoever, that's your active materials in the chemical reaction. You have two elements, PbSO4, which is lead sulfate, and water. Anybody ever see a frozen battery? Hear about a frozen battery? A battery that has been discharged and left outside during a very cold night will actually freeze. Why? Because there's no acid in the battery. It's all water. All the liquid in the battery is water. Because when the battery is fully discharged, no storage of electrons, you have a positive plate, which is PbSO4, a negative plate, which is PbSO4, and then water. If you take a battery down to nothing and it's fully discharged, 0 volts, and you hook it up to your charger, opposite directions, positive to negative, negative to positive, and you charge it up, will it charge?
Yes.
Absolutely, and you'll reverse polarize the battery. And that's because, and you'll make positive, negative, and negative positive, because it's a fully discharged battery, both plates look the same. Now, what we introduce then is an electron. So we take that and we start charging it up, and we put in the electron into this chemical reaction, right? And to fully charge it, we shove all these electrons into it and we open circuit it. So we close circuit it, shove a bunch of stuff into it, and then we open it up. That's where you see your voltage, because it's pressure, all those electrons trying to get out of it, right? You've got all that. Now, you actually have a positive plate that is PbO2. You got a negative plate, which was lead, and there's your H2SO4, which is sulfuric acid. Fully charged battery has acid, fully discharged battery does not. It's a chemical reaction. Okay? So let's talk a little bit about how this actually works. Okay? Both positive and negative are lead sulfate. We're fully discharged over here. We take our 2 electrons. We shove them into this chemical reaction. Here's what happens. those electrons, it's kind of like two people up here and they're holding hands. And Shane gets to running as fast as he can, and he comes through and he breaks them apart. That's what charging is. So we shove those two electrons in, it breaks this into two leads and two SO4s. Okay? Then it takes the water and creates two hydrogen molecules and two oxygens. Okay? So this is now what you have. But because we've introduced these two electrons that have broken those molecules apart. Now things start combining. You get your two oxygens together, because oxygen doesn't like to be by itself. Okay? So those two get together. Now your oxygen and your lead get together. That's where your positive plate comes from. Your lead is left over. It doesn't have any more oxygen to bond with, so it just stays by itself. And then all of a sudden, this H2 and this SO4, they get together. This one gets together. And now you have your fully charged battery. That's what happens every time you charge a battery. Does that make a little bit of sense? Anybody have any questions on that? Anybody bored yet? You can raise your hand. Shane's bored. Okay? But now you've stored two electrons. Now, there's a whole lot more than two electrons stored in this battery. But that's what happens on the basic chemical level for that. Okay? Does that make sense? That is what every lead acid battery goes through. It doesn't matter if it's a Crown, if it's a North Star, if it's an Exide, if it's an Interstate battery. It doesn't matter if it's the Kirkland battery at Costco. They all go through that exact same chemical reaction. That's the active materials in it. Anything else that gets added to that battery is not the active material, has nothing to do with the storage, the core storage ability of that lead acid battery. Now, there's a lot more stuff in it. And we have to build the battery, so you can't just take the chemistry. I always joke, because I work with a lot of mechanical engineers and electrical engineers on the OEM side. And so I work with a lot of them, and we always joke, and they always make fun of me, because I'm a whiteboard guy. I don't get my hands dirty. It's the mechanical engineers, electrical engineers that get all their hands dirty. And so they always make fun of me. They said, okay, it's great to have it on the whiteboard, but how do you make it actually work in real life? And that's where the construction of the battery comes in. Everybody constructs the battery a little bit differently. And we'll talk about some of the different ways the battery is constructed. So you have the core ability of the lead acid battery. All lead acid batteries are the same at the core. What changes is how they're constructed. Okay? So there's three main elements used in construction of every battery. You have the plates, where the chemical reaction takes place. You have the electrolyte, the sulfuric acid, and a water mixture that goes into it. That's very key, only in lead acid batteries. Lead acid batteries are the only battery where the electrolyte is an active participant in the chemical reaction. If I showed you a lithium-ion battery's chemical reaction, you would not see any acid. Because the acid is there as a conductive element and not as an actual part of the chemical reaction. The last piece of the terminals and case. They're the piece that all of us see day in and day out. And you'd be amazed by the amount of things oh, that's my phone. You'd be amazed by the number of things that you can tell just by looking at the case of the battery. Okay? Let's start with plates. This battery right over here is the first battery, a depiction of the first battery that Gaston Planck created back in 1859. And Alexander, the Europeans pronounce it differently. Alexander Volta actually came up with the concept of batteries. Anybody know how he came up with the concept of the battery? Dead frog. Didn't expect that, did you? Dead frog, he saw a frog on the ground, dead, and guess what was happening? His leg was twitching. He knew that the only way your body can move is if you have an electrical impulse being sent to your muscles, which is a chemical reaction as well. That electron has to move within the muscles. So he knew there was even though it was dead, it could store electrons and move electrons. That gave him the idea for a battery. Started creating batteries. Gaston plant created the very first lead acid battery, which actually utilizes lead rods. And up until, I want to say it was the 50s, there were still batteries built with lead rods. So what they did was, he understood that the chemical reaction is the key to every lead acid battery. So he said, okay, I have the lead rods. How do I get more storage ability? Do I add more rods? Makes more sense to make those rods have more surface area for the more chemical reaction to happen on those same rods. So he started grooving them. He started doing all kinds of things. Then he came up with what we call the plant plate. The plant plate is actually, and you didn't even read it, is actually a grid structure that's perforated or cut out to be able to hold a more porous material. So the plates that are used in batteries today, the concept of them came from, we used rods first, we grooved them, we did everything. We wanted more surface area for that chemical reaction to take place. We needed more surface area. So they came up with the idea of, okay, let's make it into like a paste. So it's very porous, it's like wet sand. And you can have that chemical reaction happening all in there. But if we do that, it can't just stand up in the battery. What do we put it on? We put it on grids. That's what a plate is made of. A plate isn't just a grid that looks like that. It's also pasted with the active material for the chemical reaction to happen. The chemical reaction doesn't actually happen on that grid. That's just a conduit for the electrons to get into and out of the plate. But the paste that goes on top of that grid is what it is. Okay? Now, over time and things, and if you don't build your grids the correct way, you can actually start having slippage, or that material, that active material, flaking off. We call it shedding. And during the chemical process, it'll move around. Under heavy vibration, it'll shake loose. In a flooded battery, there's actually a sediment chamber on the bottom of the battery. I've heard it called a crap catcher, and a mud well, a bunch of other things, because the plates don't go all the way to the bottom, so that if that material starts shaking off and coming off, it goes to the bottom and it's held in the bottom. And doesn't short out the battery. It doesn't actually touch the plates. It falls into the bottom. So, but that's the plant plate. Everybody's using plant plates nowadays. Now, how they build them is very different. Chip builds his plates differently than we build our plates. Well, Chip doesn't build it. Chip's not a dirty hands type of guy.
Oh, whiteboard guy, dude.
Yeah. So, Chip's company, they actually coin their grids. Now, the way they do it is slightly different. So they just don't punch it. We punch ours, which means we take a really long sheet that looks like a long sheet of tinfoil. It really does. It looks like a long sheet of tinfoil. We put it through this machine and we just boom, 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 punch out a bunch of grids. He doesn't. He actually coins his grids so there's more texture to them to hold the material better. Now, we build different types of batteries. Mine are high compression batteries. His aren't as high compression batteries, so he needs to make sure the material stays on much better. He coins his grids. We punch ours. They're very different techniques, but they all do it a little bit differently. Every manufacturer does a little bit differently, which is why you can have two batteries that look the same that perform differently. Okay? Any questions on plates? Positive and negative plates are built almost identically, even though the positive plate is much more important than the negative plate. Okay? Now, once we build them, we start constructing the battery itself. The plates are very important. Sub-assembly at a battery manufacturing plant typically will take up more space than any other part of the assembly up until formation. So it will take up a big part of it because you have to bring in all the lead, you got to mix everything, you got to do your acid, you got to put it all together, and you paste them. So what we do is we paste these plates, we put them in the ovens, we dry them, make them hard, then we stack them. We go positive, negative, positive, negative, positive, negative. Put a piece of paper in between them called a separator to make sure they never touch, so the chemical reaction can take place. Okay? We good? Yeah? Nobody's asleep? Let's talk about the electrolyte. The electrolyte, and we call it electrolyte, we don't call it acid, because it's a mixture of acid and water together. Now there's a lot of different things that can go into that electrolyte. Okay? You can use specific grades of sulfuric acid. So you can have a very high medical grade of acid to start out with, and then you start cutting it down with water and diluting it and putting it in, and then you get to the kind that you want to use. And then you put it in with the, to help mix that paste. It's used as part of the paste mixture to make sure that we get the plates correct, or the plates pasted correctly. Then after we assemble the entire battery together, we put the electrolyte into the battery so the chemical reaction can take place. The electrolyte, you start with a specific acid, you cut it down, so you have an initial purity, and then you cut it down, and then you have what we call saturation level at the end. And that's the amount of water to acid that's in that battery. It's very critical. This same concept was used in the lead antimony batteries that used up all that water before. Anybody ever rejuvenated or heard of the rejuvenation of a battery where you used to pop off the caps and pour water in and all of a sudden it worked again? What happened was acid saturation level is very important in the battery. The higher the saturation level, the more acid to water. So if you have more acid in that battery, you'll get a higher capacity. As you lose water over the life of the battery on those lead antimony batteries, as you lost that, it would start right here and it'd start creeping up. It'd start creeping up. And then you're telling me, but then why did it go dead? Why wouldn't it start the car if you were getting higher capacity? Because the capacity didn't last long enough. You would actually have a huge capacity, but you couldn't hold it long enough for the car to crank over. That's why it wouldn't work. Now you start adding water to it, pouring in a called Motorola. Anybody ever heard of it? In the 80s, Motorola said, you know what, we got this great new product. We're going to put everything we have behind that product. Guess what that product was? The StarTAC phone. Anybody remember that StarTAC phone? Yeah. They decided they were going to start putting so much effort into that they started divesting of a bunch of other patents they had. There was a gentleman by the name of Steve McShane, lived in the Chicago area. What he did was he worked as an engineer for Motorola for a number of years, and he ended up leaving Motorola to start up his own business. He started up a business by Midway, called Midway Electronics. Midway Airport, if anybody's been to Chicago, is on the south side. It's in a very industrial area. He opened up a CB radio repair business. He was an authorized repair facility for Motorola CB radios, and he had friends still at Motorola. And a couple of them came to him and said, hey, just so you know, we're getting rid of all these patents, and we're doing it real cheap. He found a patent that was developed by a gentleman out of Minnesota for the application of Ohm's law as it applies to obtaining conductance and how that relates to conductance is the inverse of resistance and how that relates to batteries cranking ability. He said, you know what, I can do some of this. Bought it from Motorola for $20,000. Midway Electronics quickly transformed by the early 90s into Midtronics. Midtronics today is the leading manufacturer of electronic battery testers worldwide. They took that one patent and developed it into a way of identifying the starting ability of batteries across the marketplace. Now, that sounds like a wonderful story. The only challenge you have is Ohm's law is more than just one element. There's a whole lot of other things that go into it. And as batteries changed, it made that algorithm more and more difficult to apply to batteries. Today, a Midtronics tester, there's not a single Midtronics tester in the world today that can test a pure lead AGM battery. They're not very accurate today because of changes in manufacturing technologies on brand new batteries. Thus, on Midtronics new tools after, say, 2005, they actually have a new battery test versus a regular battery test. You're like, but why would you separate the two? because they weren't very accurate on new battery tests, and so now they're just looking at voltage on new battery tests. Electronic testers, while easy to use and readily available, can be challenged, especially with newer battery technologies. Doesn't mean that they're a bad thing to have. I helped design them and work with them for many, many years, and to this day, we have ones that we recommend and we tell people they should purchase, because they actually do fit a role in the marketplace very well, especially with unskilled or underskilled technicians when it comes to batteries. Battery specialists, you'll rarely see them using a Midtronics tester other than just pre-screened batteries. They're typically using load testers. Now, that came out in the 80s and into the 90s, and it wasn't until the 2000s that it really caught on. But it has now developed a new area of hybrid testers. And that is some companies that have decided, we're going to make something that looks like a load tester, but because batteries now have a whole lot more cranking ability than they used to, we don't want to be this battery right here has an 1150 cranking amp rating, 1150. What's that mean a BCI load test should be? 5.7. You know what? And nobody pulled out their phone. Good job. I've done many classes with everybody. Immediately ask them a math question. 575. There are no load testers on the market, very few that are affordable, that are over 400 amps. So what do you do to run a BCI load test on something like that? You can't do it with one of those. So these hybrid battery manufacturers decided, oh, we got an idea. We will only put 400 amps on it, but based upon it getting to, let's say, 10.5 instead of 9.6, now we can say the battery's good. It's not a BCI load test. It's a hybrid test. It's a version of putting a load on a battery, taking the information back, and then running it through an algorithm and coming up with a result. Autometer does this. Autometer has built a phenomenal business based upon this. Okay? Any questions on testers?
How about the electronic battery testers, when you do the full system test, does it do a decent job of testing the full system?
Depends on the algorithm. Yes, it does a better job on the system than the battery, because it exercises the system. Most of the time they'll have you rev the engine, turn on loads, off loads, those type of things. You're exercising the battery, not just running a signal through it. They do a pretty decent job. Some of them have gotten to the point where they try to diagnose open diodes and things like that. And that's fairly accurate. I like system testers or electronic testers more than I like battery testers, the battery test functionality.
So in your opinion, you would, if you're using a full system tester that also checks the battery, like Midtronics tester we have, you wouldn't trust the battery test on it?
You get some struggles. If you put a Midtronics tester on a Northstar battery coming right off a charge, it's going to say unstable battery, because it's sitting up 13 volts or above and it doesn't know what to do with it.
Yeah.
So yeah, electronic testers. Electronic testers are good at the right situations. All day long in a quick loop, in a quick check, in a pre-screen environment. Actual diagnostics of understanding what's wrong with the system on a discharged battery, whether it's a battery, whether it's alternator, whether it's voltage drop, whether it's something, I don't trust them.
We've gone back and forth and we've gone to our SP5.
I like that tool.
Several times and proven the battery to be okay.
So just how accurate is field testing? This is where it comes into it. So there are three elements that every tester is going to look at. Okay? Ohms. Are you talking about my cartoon back there, Jeff?
That's very appropriate.
That's not inappropriate. Now, if I put names next to all the people, that would be inappropriate. So you've got ohms, which is your resistance, which is the inverse of conductance. So all that resistance is 1 over conductance. That's all it is. They're just flip-flops of the two. You have your amperage flow, and you have your voltage. All testers nowadays are doing these three things. It doesn't matter if it's a load tester, it doesn't matter if it's an electronic tester, it doesn't matter if it's a hybrid tester. They're running it through algorithms or you're doing it through a test procedure to identify those three elements and make a decision on the battery. Okay? Anybody know where those three elements came from? Ohm's law. Anybody ever seen this circle before? Other than Dan. This is Ohm's law. Everything that has to do with electrical on batteries comes back to this. Okay? Ohm's law identifies four pieces. Voltage, which is pressure of the electrons trying to get out of the battery. Amperage, which is the flow of the electronic batteries when they're released from the battery. Resistance, which is the resistors, or I can't think of a better word for it, the blocks that are trying to keep the electrons from moving through, and wattage. Wattage is the power of the battery. This is a very elusive thing. The reason why your wattage or your power isn't over there where the testers are, because there's not a tester today that can effectively tell you your power. You know what that is? That's a reserve capacity tester. Even the ones that are out there, which are discharge testers at 25 amps or 75 amps, aren't always accurate because, again, you got to maintain the right voltage thresholds and constant current and all this kind of stuff. But anyway, those elements are what make the battery testers do what they do. How well they do that really depends on the type of battery. Chip will have a different recommendation than I do. I will have a different one than Interstate does. You will find that every battery manufacturer will have a different recommendation on battery testers. Why? Because number one, we want the battery tester to make our batteries look as good as possible. But number two, every battery tester is based on one of these three elements. And based upon how you manufacture and design that battery, these three elements are going to change. And therefore, to try and develop algorithms to cover every single battery, what happened?
Oh,
Did it say?
this guy down here, you know.
I heard it ring, but did it say something after it? What did it say?
That was Siri.
Oh, Siri said something? She's funny. But those three things are different for every battery. For instance, resistance. Chip can tell you his resistance in milliohms for each one of his batteries. It's different for each battery. Our Group 31 battery has 2.2 milliohms of resistance. Okay? Resistance is based upon plate size. So the larger the plate size, the lower the resistance naturally. Which means if we make a shorter battery, it has a higher resistance. Now, if you've got a conductance tester, which is the inverse of resistance, and you try to put the same algorithm on every battery whenever the resistance is different on every battery, all kinds of things can adjust. Any questions on testing? Yes, Jim?
Just talk briefly about the connection point with the electronic tester, Jeremy, with stud versus post and the rest of that.
So going back to the electronic testers, they're based off of conductance, which is the inverse of resistance. Resistance inside a battery is based on chemistry. And by that, anybody ever wonder why, well, you probably don't even know. We employ, every battery manufacturer will employ metallurgists. Anybody know what a metallurgist does? They deal with alloys and things like that. The biggest key in any battery is that resistance level that's inside the battery, right? And to the outside of the battery. So anytime you increase that resistance over the life of the battery or anything, you're going to end up failing the battery. Electronic battery testers, if you hook them on to a steel post, steel has a very high resistance level. Now you're not taking a look at how good the battery is. What are you taking a look at? How good the steel post is. And who cares, right? Because your connection is never on the steel post. It's at the pad. That's why you have to, if you're using an electronic battery tester, you take those lugs and you screw them down. That gives you your connection to the pad to test it. Okay? So anytime you're testing with an electronic battery tester, know that you're looking for resistance. Anything that is a resistor outside of the battery is going to throw off your reading. Corrosion, that's why you want to clean off the corrosion before you test with an electronic battery tester. Because otherwise you're seeing the resistance from the corrosion degrading the battery, and that's not the case. Make sense? Is that what you wanted? Beautiful. Any other testing questions? I want to leave you with one thing. And by the way, this is the atomic model of lead. And if anybody would like to go through a class on valence electrons and how electrons move between the two, I can come back, be more than happy to. Okay? So a proton and a neutron are walking down the street. Proton says, wait, I dropped an electron, help me look for it. Neutron says, are you sure? Proton replies, I'm positive. Thank you guys very much, and I appreciate your attention, and nobody fell asleep that I know.
Just a couple of quick comments.
Can I ask you a question that's on my mind? You're
Yeah.
talking about testing and all that other stuff. What about the difference now that you're seeing in the chargers? When you do bring your batteries in, you're charging them, there's specific AGM, specific these. Is it just voltage variances in those batteries?
Yeah, everything that has to do with batteries nowadays is voltage regulated. So whenever it comes to your marketplace, voltage regulation is the key whenever you come to charging. That's why you see those difference in the thing. So you want to regulate the voltage. So a battery is very similar to filling up a water balloon at the spigot. Do you guys use the word spigot? I'm always curious. Do you know what a spigot is? Water spigot?
Yeah.
Good. I've said spigot before and people look at me, what's that? So you take a water balloon, you put it on the spigot, right? And you turn it on just a little bit. Does that water balloon ever fill up? It doesn't. And let me explain to you why. Because what is required to make that water balloon fill up? Pressure to expand the balloon. And if you just turn it on a trickle, it will never give. What will happen is the pressure of the balloon will actually push back on the pressure of the very low pressure coming out of the faucet and actually stop the water flow. And it won't actually expand because the need to expand the water balloon has a specific pressure. If you're putting out less pressure here than what is required there, it will never fill up. Same thing with a battery. If you use less pressure putting into the battery, then the battery needs to start expanding and accepting the electrons. Because remember, you're shoving electrons in there. If you use less pressure to that, it will never charge back up. If you take a very low resistant battery, remember, whenever you shove electrons in, pressure is pushback, right? If you have resistance, it pushes back on those electrons, causes voltage. Voltage goes up. If you have a low resistance battery, like a pure lead AGM battery, that's at 2.2 milliohms, and you put 2 amps into it, there's no pressure buildup anywhere. So it will never actually fill up with electrons because it starts pushing back.
What kind of spigot are you using that you can adjust the pressure? And not
The manufacturer, if you look at their battery application manuals, they'll actually tell you what they recommend. On Northstar Group 31 actually requires 7.5 amps per 100 amp hours as a minimum. That's a minimum to get the pressure to the point where it can eventually absorb it.
75 to 100?
Oh, that's beautiful.
No, is that what you said?
No, 7.5.
7.5.
Yeah, that's beautiful. We get calls, and I oftentimes have to take the technical questions that come into the factory. And by the way, the consumers who call a factory with questions, especially on batteries, they are special people. They really are, because they want to know everything there is to know. And I'm on the phone, and I'm not a great communicator. So anyway, so they often call in and say, I've had my battery on charge for a week, and it's still not charging. What kind of charger? I've got this half-amp charger, Sears Die-Hard charger that I bought back in 1983, and it's worked for me all this time. It's a half-amp charger. What's the voltage at? 9. It won't come off of 9 volts. The battery's 9 volts. It won't come off of 9. It needs more amperage. Well, why? Then I have to go into Ohm's law, and I can never explain anything simply. So every manufacturer, based upon the resistance of their battery, is going to effectively tell you what it is. Now, on the high end, the reason why their voltage regulation, that's from an amperage standpoint. On the voltage regulation standpoint, an AGM battery doesn't want anything more than 14.2 volts. Pure lead AGM wants 14.8. A flooded battery is typically 15.5 to 16.5, much higher. Why is that? that they can allow more. The challenge you have when you have an acid-starved AGM battery is it's about the path to get the electrons to store inside of it. Energy cannot be created nor destroyed. All the amount of energy that is in our world today is the same amount that was in our world 1,000 years ago. It transfers forms. So you're taking electrical energy and you're transferring it into chemical energy. However, if it hits resistance and it starts pushing back, what happens to your voltage? Goes up, right? But you continue pushing that amperage into the battery. The resistance of the battery pushes back, so it can't be accepted in the chemical energy. You've got electrical energy, and it's just electrons following electron. You've got a traffic jam. They're not going anywhere, and everybody just keeps running at it. Where do you think those electrons go? Where do you think that energy goes? Thermal energy. Battery heats up. When you heat up the battery, you keep oxygen and hydrogen in their gas states. Now, whenever that battery, hydrogen and oxygen have to recombine, right? Whenever there's left in gas states, they can't recombine and fall back into the electrolyte. Therefore, it stays in a gaseous state and it builds up pressure until they have to leave. As soon as that hydrogen and oxygen leave, it's mostly hydrogen, leaves, you don't have that water. What happens to your electrolyte? Saturation level goes up. See how it all works together? That's why if you voltage regulate, you will never overcharge the battery. Anybody ever hear of a battery exploding?
Oh, yeah.
It explodes while on charge because they're overcharging and the voltage is too high. Hydrogen in gas form is escaping the battery, a spark ignites it. There's a lot of things that go on to it, but it all goes back to that chemical equation. Does that answer your question?
Comes to a wheel charger where there's no regulation going on, and they're just cranking power into the battery to get the vehicle started.
So let me ask you another, this might be a stupid question. What happens if you have a car and you change the type of battery? You go from a lead acid to a AGM.
You can always go from flooded to AGM. You can never go backwards. So if you have an AGM-based vehicle, Mercedes has moved all AGM batteries. If you have a Mercedes passenger car that has the battery under the seat, you actually have to keep an AGM battery in there.
Is that because of charging?
The charging system is based upon that chemistry of battery, and therefore you can always move up in technology, you can't move backwards. In fact, it was about maybe it was longer, maybe 6 months ago, there was actually a mother and daughter that died in their vehicle because they bought I can't remember if it was a Mercedes, but it had a battery inside the vehicle. It's the first time anybody's ever heard of this actually happening. But the used car lot put a flooded battery in for the AGM battery. Flooded batteries aren't vented. They started overcharging the battery, gassing. They passed out. They pulled over. They were feeling sick. They passed out. They had no idea it was because of the battery. But 2 people did pass away. It might have been late last year, but it was all over the news. In the battery world, it was big news. Probably not in your world. I live in my own little world. So.
All right, we're going to take a break here for 10 minutes. But before we do, I just want to comment on this Medtronic